Assalamualaikum warahmatullahi wabarakatuh. My name is Noor Azhar Azhar and my metric number is TE180152. Okay, for this PBL, the students will be required to study about the PID control and what is functions of the PID controller basically. So about the PID controller, this is for stabilizing the control system, for obtain the desired output as or reference. So basically this PID controller, the students need to the calculated PID and compare it with the simulations. Okay, back to the PID controller, which is the PID controller is a closed loop system which has a feedback system, and the feedback system need to calculate the process variable, and if there is an error to achieve the desired output, the feedback system will be the one with calculate and reduce the error signal by adjust the output system. So this process will go on until the error gets 0 or the process variable is equal to the set point. Okay, so back to the question, which is the question is about an opening door control system, which is employed by the gears, the pulley, and the door itself, and then with amateur DC motor. Okay, so the body diagram would be like this, which is it could be have a damper in a load at the motor at the input, which is basically with we will have the circuit of DC motor, and then it connected to the inertia, which is J, and the damper and the gear itself, so the gear N1 and N2, and it goes to the inertial load and back to the damper and so on. So this question required the student to find or determine or compare the PID results from the simulation and calculation by using a calculation from the body diagram, and then do the mathematical derivation or mathematical modeling. And by using mathematical modeling, we need to find the stability of this process by using the Routh-Hurwitz stability system, and then the last one would be the PID calculation. Need to find KP, KI, which is the gain for proportional, the gain for the integral, and the gains for the derivative. So KP, KI, and KD needs to calculate it to find the P parameter, the PI parameter, and PD parameter, and so on, the PID parameter. Okay, that's all. Okay, let's continue to the calculation.
Assalamualaikum. My name is Noor Faradilah Afiqah Binti Hasan. My metric number DE180186. And now I will explain to you the mathematical model derivation from the door opening problem, where we want to find the input, which is rated motor terminal voltage VA, and the output, which is the door position theta L. After that, we want to find the stability of the system. After that, we want to find the P, PI, PID, and PD controller value. So let's start. So we are given a project for the door opening control system. So this is the door opening control system, and then we modeling it into a electromechanical system element, and we are given a data for the DC motor data and the gear data. For the mathematical model derivation, we want to find the theta L over VA. So we want to find the VA. VA is the equation that we get from the electric circuit. Then TM is KA IA multiple with IA. And then we get use IA as a subject for equation 2, and then EB as equation 3, and TM equal to JEQ S square plus DEQ S theta M as a 4 equations. Then we put the equation 3 and equation 2 to equation 1, where we get this equation for equation 5. Then we put the equation 4 into equation 5 and we get this, and we declare it as a sixth equation. For mechanical analysis, we know that TL over Tm equal to the theta L over theta M, which is equal to N1 over N2. So we want to find the rotational of load theta L is converted to motor shaft. So theta M equal to N square over N1 multiple with theta L as a equation 7. Next, we put the equation 7 into equation 6 and we get this equation for theta L over VA. After that, we convert it into a block diagram, which is like this. As from the equation above, we want 1 as a numerator, so we divide the KA at the denominator. So we know that where the JEQ equal to JM plus JL multiple with N1 over N2 square. So we get this answer is 0.2221, and then DEQ equal to DM, but DEQ is not considered because the number is so small. And then we substitute the value and we get the answer, which is theta L over VA is 1 over 0.315 s cubed plus 29.151 s square plus 18.75 s. Next, for the stability of system, to analyze the stability of the system using Rothe-Hurwitz table with the obtained transfer function. So from the transfer function given, we declare it as a GS. So we want to find the transfer function. So this is the formula of the transfer function. After that, we substitute the value and we get that the Kp, the transfer function, which is Kp over 0.1315 s cubed plus 29.151 s square plus 18.75 s plus Kp. From the data given, we put the data into the Rothe area table, and then we know that the for stability, Kp must be positive and all the elements in the first column must be positive. Therefore, there are two conditions. One condition is Kp is more than 0, and second condition is Kp is less than 1735.17. So this is the range of the Kp. We want to find the value of P, PI, PD and PID controllers to use for the simulation. So first of all, we want, from the Rothe array above, we can find the K critical. So we know that the K critical equal to the Kp. So the K critical is 1735.17. By using the even equation from the Rothe array, substitute the K critical using complex domain to find omega critical. So we know that the even equation is 29.151 s squared plus Kp. And then we change the s square into the j omega form. After that, we substitute the value of Kp and we know that the j omega equal to -1. So we substitute and we get that the omega squared is equal to 59.523, and then we want to find the omega only. So we get the answer is 7.715. But from the omega, we want to find the time. So we declare as a TU. So to find TU, we use this formula and we get that TU is 0.8059. We want to find the P parameter, PD parameter, PID parameter and PID parameter. We use a Ziegler-Nichols method. So to find the P parameter, Kp must equal to 0.5 multiple with K critical, and we get the answer. After that, we want to find the PI parameter. So we use Kp equal to 0.45 multiple with K critical, and we get the Kp is this answer. And we want to find the Ki. Ki is 0.54 multiple with K critical over Tu. So we get the answer. Then we want to find the PD parameter. We use for the Kp, we use 0.5 multiple with K critical, and we get this answer. And we want to find the Kd. Kd is 0.54 multiple with K critical and multiple with Tu, and we get this answer. Lastly, we want to find the PID parameter. So for Kp, we use a 0.6 multiple with K critical, and we get the answer. For Ki, we use a 1.2 of multiple with K critical over Tu, and we get this answer. And for Kd, we use 0.6 over 8 multiple with K critical and multiple with Tu, and we get this answer. So that's all for me. Thank you.
Assalamualaikum, my name is Athira Nabilla Binti Omar, and my metric number is DE180172. So today I will explain about the simulation for this project. As you can see from this graph, the steady state area in this system is decreased. So the output value of this system close to the desired value. So the transfer function of the calculated and the automatic system is almost the same. For the proportional gain is same for both graph. For the second one, I want to compare the graph for proportional integral controller. As you can see, the calculated graph and the automatic graph is slightly different. So, which is the rise time for the calculated graph is lower than the automatic graph. So, the automatic graph need more time to rise than the calculated one. Next, I will compare the graph for proportional derivative, which is PD controller. Okay, for the PD graph, you can see the result is almost the same. This is because the bigger the derivative, the smaller chance to have a steady state error. So the both Kd and Kp is the same value. The last one, I want to compare the graph for PID, which is proportional integral derivative controller. So PID. As you can see from the PID graph, the auto-tune rise time is more slower than the manual one. This is because the manual one is fast to meet the settling time rather than the auto-tune. As you can see from the table, the overshoot percentage is increased by reducing the rise time, such as a tune response need 1.16 seconds of the rise time to achieve the maximum overshoot percentage, which is 8.09%, while the manual response just need 0.0366 seconds to obtain the overshoot percentage, which is 6.12%. The value of P, I, and D and tune also different to obtain the stable door opening system. The conclusion of this project, the process of door opening control system, we can obtain through PID controller using Ziegler-Nichols method. In order to get the value of P, I, and D, we have to calculate and get the Kd, Kp, and Ki first, and then based on the value that we get, we can calculate manually, or we can also using MATLAB to auto-tune. So to minimize the rate of PID loop until overshoot can be done by set the gain of PID controller to half of the value. then adjust the reset time so it's correct for any offset within an acceptable period. Basically, the both method, which is auto tuning or the manual calculation, is have a same performance to get the rise time, to get the settling time, the overshoot percent, and the difference is how they operate, such as manual tune. We must set one by one, but the auto tuning, we just set in the PID controller and run the simulate. Also, the both method use the same rule of calculations. The difference is not so big because the rule of calculation is almost the same. So that's all from me. Thank you.